This story goes back almost 2,500 years ago, and it started when the Greek philosopher by the name Aristarchus came up with what we now know as the heliocentric model of the solar system. In the heliocentric model, the helios, that is the sun, is believed to be at the center of the solar system, and everything, including the Earth, is assumed to revolve around the sun in circular orbits. Almost 400 years after Aristarchus coming up with his heliocentric model came the Ptolemy's model, Ptolemy with the P silent. Now, Ptolemy came up with a differing model. His model had the Earth at the center and everything, including the sun, revolving around the Earth. Now, the Ptolemyan model was known as the geocentric model because it placed the Earth, that is the geos, at the center of the solar system. Unfortunately for mankind, it seems that the wrong one, we know which one is wrong, the wrong one went into the religious texts, some religious texts, and became a hurdle in the development of science. The story then moves on to what we know as the European Renaissance age, and that's when the development finally began. What I believe is the most exciting era in human history, the European Renaissance era. And in the beginning of that era, a European mathematician, astronomer, physicist by the name Nicholas Copernicus confirmed with his observations that it's the heliocentric model that's correct. His confirmation was based on certain observations that he made. The observations, as you can see in this animation that's playing to my right, you can see in this animation that if you assume that the planets and the sun, everything orbits the Earth, then we have a difficult problem to explain. Because if you look at the planet Mars, it appears to move in a very funny manner. It moves away from the Earth, then closer to the Earth, and when it is closest to the Earth, it almost seems to move backward and then starts moving forward back again. Now, this was a very difficult thing to explain using any common sense laws of physics. It was far too complex a motion to be natural. Copernicus then used the heliocentric model to try and explain what was going on. Now look at the animation to my right, and in this animation we are assuming the sun to be at the center and the Earth and Mars to be revolving around it. Now if you look at these motions and placing ourselves on the Earth, हम अपने आप को अर्थ के ऊपर रख लेते हैं, we place ourselves on the Earth and then keep looking at Mars. Can you now see for yourself that the motion that we saw in the first animation is actually how Mars appears to move from the Earth when we look at Mars, while Earth and Mars both revolve around the Sun. Now this motion, the retrograde motion of Mars, as it appears to come closest to the Earth, it appears to move back and then back in the forward direction later. This motion could easily be explained assuming the heliocentric model, the sun at the center model. So this became the basis for Copernicus to promote what was then popularly called the heliocentric model or sun-centered model. Then comes Galileo, a man for whom we will run out of adjectives, run out of words to explain his greatness. He was regarded as the father of modern science, father of modern physics, father of observational astronomy and whatnot. An amazing man who gave further evidence for our heliocentric model. Now, the evidences that he gave, in addition to what Copernicus had already given, he observed the motion of the moons of Jupiter. And from his observations, it appeared that those moons appeared to go behind Jupiter and disappeared for some time. This could only be explained if those moons were orbiting Jupiter, which meant that there are objects in the solar system which do not orbit the Earth. Remember, the geocentric model places the Earth at the center and absolutely everything revolves around it. So, Galileo's observation of Jupiter's moons contradicted this belief. Then he also made another very interesting observation. He looked at the planet Venus and he observed that it appeared to show phases just like our moon. Now, these phases could only be explained if Venus was orbiting the Sun while we observed those phases from the Earth. This observation, along with Copernicus's earlier observations, absolutely established what we now know as the heliocentric model to be correct. Unfortunately, for Galileo, this also proved to be a problem. There was this famous European Inquisition in those times, and he was tried and convicted of heresy, and he was sentenced eventually to life imprisonment. He spent the rest of his life in house arrest, but he continued his prolific work of writing. Never once did he believe that he contradicted the Bible. In fact, he believed that what he said could very well be interpreted as what was given in the scriptures. So Galileo was indeed this very brave person who actually risked everything that he had, including his own life, to promote the cause of science. The Galileo story is in fact a very, very interesting one. When his injunction was on, he was forced to take his words back in public, which he of course did. But then it is rumored, or perhaps it actually happened, that when the crowds were gone, Galileo is supposed to have gone to the judges and told them, how does it matter what I say? The earth moves. It's a legend. If it was true or not, no one really knows for sure. Now comes Tycho Brahe. And Tycho Brahe was a European astronomer and was on a mission to actually prove the Bible right. And he made observations of the planets that could be seen from the naked eye for almost 21 years. And he actually went underground, and here's the equipment that he used. The equipment was kept underground because in the winds, buildings tend to shake a little and the observations become a little inaccurate. So he went underground with this equipment and made the observations of the planets. For 21 years he made these observations and then passed these observations on to his student Johannes Kepler, who then made the analysis of those observations, finally arriving at what we now know as Keplers Laws of planetary motion. Now, Kepler was pretty much the person responsible for the 17th century scientific revolution. He pretty much heralded this scientific revolution. He came up with these three famous laws of planetary motion, the first one of which is called the law of our orbits. Now the law of orbits says that all planets, including the Earth, revolve around the Sun in elliptical orbits, with the Sun at one of the foci. Foci is, by the way, plural for focus. So according to Kepler, all planets, and all planets includes the Earth, revolve around the Sun in elliptical orbits, not circular orbits as mentioned in Ptolemy's model. They orbit the Sun in elliptical orbits, and the Sun remains at one of the foci of the ellipse. Now the ellipse, as we all know, is a very interesting curve. Now let me describe an ellipse for you. Back in those days, ellipses were drawn in a very interesting manner. Points F1 and F2 that you see in this diagram on my right, those are called the foci, or the focuses, if you can use the word, foci of the ellipse. F1 and F2 are the foci of the ellipse. Now two nails would be hammered into the ground at those 2 points, and a thread loop would then be created. Now, keeping the thread loop tightly going over the nails at the foci, the thread loop was tightened and a pencil would be inserted inside the thread loop at point P. Now, the thread loop would be tightened and the pencil would then be made to move on the ground or on paper, and this would create an ellipse on the paper or on the ground. So in an ellipse, it's a curve basically for which the sum of these two distances F1P and F2P remains constant for all the points on the ellipse. That's an ellipse for you. Now the line joining the two foci, F1 and F2, that line is called the major axis of the ellipse, and the perpendicular bisector of the major axis is called the minor axis. Now the half length of major axis, as depicted by A in this figure, is called the semi-major axis, and half length of the minor axis depicted by B, shown as B in this diagram, is called the semi-minor axis. The semi-major axis and semi-minor axis A and B are then used to write the Cartesian coordinate equation for an ellipse. The Cartesian coordinate equation of an ellipse goes like this, as you can see in the diagram on my right: x square by a square plus y square by b square equals 1. Now interestingly, a circle is a special case of an ellipse where a and b would be equal, and they would then be equal to the radius of the circle. Now the next law that Kepler gave was called the law of areas. As far as the law of areas is concerned, it says that the radius vector that you draw from the Sun to a planet sweeps out equal areas in equal intervals of time. Now, in slightly different words, we can state this law as saying that the area swept by the radius vector from the Sun to a planet sweeps out equal areas per unit time as it moves along in the orbit. So, as a planet orbits the Sun, the radius vector sweeps out a constant area per unit time in the orbit. Now, the area swept by the planet per unit time is called the aerial velocity of this planet. Now, let's calculate this aerial velocity, and we will keep this aerial velocity result with us for our future discussions on this particular law. Now, if you look at the diagram on my right, let's assume that the planet moves from point A to point B in time delta t. Now, in time delta t, it will move a distance v delta t, where v is its velocity. Now, we've drawn a triangle between A, B and the Sun. Now, if you extend the base of the triangle, that is AB, and drop a perpendicular on that base from the Sun, this perpendicular turns out to be r sine theta, where theta is this angle you can see between this radius vector and the velocity vector. Now, if you know the formula for calculating the area of a triangle, now this formula says half times base times altitude. Now, the base of this triangle is v delta t, and the altitude of this triangle, as you can see, is r sine theta. So, the area delta A of this triangle is half times v delta t times r sine theta, and therefore the area swept by this radius vector per unit time, that is delta A by delta t, comes out to be half v r sine theta. Now, please make sure you remember this particular result, because we are going to make good use of it in time to come. The third law given by Kepler is called the law of periods, and this law states that the square of the time period of revolution of a planet around the Sun is directly proportional to the cube of its semi-major axis. So, if t is the time period of revolution of a planet, then t square is directly proportional to a cube, where a is the semi-major axis. Now, these three laws that Kepler gave, the law of orbits, the law of areas, and the law of periods, they became the foundation for Newton's law of gravity. And that's the reason why I have introduced these laws at the beginning of this series of videos rather than at the end, as is given in most physics textbooks. It makes more sense to study them right in the beginning, and then we find the explanation that Newton came up with for these laws. These men who studied these phenomena, who looked at the skies above and broke the code about their motion, broke the pattern that they followed, these were brave men, because they risked their lives, because somewhere they knew that certain orthodox religious people did not like what they were saying. So they advanced the cause of science, often even risking their lives. And these were the giants on whose shoulders Newton stood to be able to see farther than anyone ever saw. When he was in fact asked as to why he could see so far when no other person could, Newton said, "I could see far because I stood on the shoulders of giants." And Galileo, Copernicus, Tycho Brahe and Kepler, these were the giants on whose shoulders Newton once stood to discover his law of gravity. And that will be the topic of our discussion in the next video. So please wait for this next video from the Physics channel. Keep watching our videos, keep enjoying them. Please do provide with feedback on how you found this new format of the video, and we will meet again. Bye-bye.